Rhythmic activity is a widespread and very important phenomenon within the nervous system. Many of the activities that animals perform, such as locomotion, ventilation, peristaltic gut movements, and copulatory movements, are all rhythmic. There's considerable interest in how such activity is generated. It's now known that in many cases the fundamental rhythmicity can be generated within the central nervous system itself, without requiring the participation of either muscles or sense organs. Of course, in an intact animal, the peripheral components may have profound modulatory effects, and these may be crucial to the success of the behavior which actually employs the rhythm. But nonetheless, it's an intriguing reality that in most cases the central nervous system alone can generate a rhythm which is recognizably related to that of the intact animal. The neural elements that are involved in generating such rhythms comprise what are known as central pattern generators. There are two conceptually distinct mechanisms of central pattern generation. First, there may be a circuit in which no single neuron shows any rhythmic behavior. The rhythmicity arises from the connectivity of the circuit. These circuits are called network oscillators. Second, individual neurons themselves may show rhythmic bursts of spike activity without any input from other neurons. Such neurons are called endogenous bursters. In this tutorial, I will show you how to build a variety of network oscillators within AnimatLab. A separate tutorial will explore how to create endogenously bursting neurons. Let's begin by creating a new project. A copy of this project is available at Program Files, AnimatLab, Tutorials, Neural Networks. Please choose where you want to create the project and then name it Network Oscillators. Once you have the project, please add an organism and open its behavioral editor. We need to add two spiking neurons and modify them slightly. Change the threshold to negative 55 millivolts. Accommodation to 0. The after hyperpolarization time constant to 5 milliseconds. And add a tonic current stimulus of 6 nanoamps. Now draw a new synaptic connection from neuron 1 to 2 and select the hyperpolarizing IPSP synapse type. Change the conductance to 1 microsiemens. The decay to 20 milliseconds. And set facilitation to 1. Now add another hyperpolarizing synapse from neuron 2 to 1. When two neurons inhibit each other in this way, it's called reciprocal inhibition. Now we need to create a new line chart to view the membrane voltages of our neurons. Set the end time to 2 seconds. Change the points to keep to 15,000 and set the update interval to 100 milliseconds. Next, we need to add some stimuli. Add a tonic current stimulus to neuron 1. Keep the start time at 0, set the end time to 50 milliseconds, and leave the amplitude at 10 nanoamps. Add a tonic stimulus to neuron 2 as well. Set the start time to 700 milliseconds, end time to 750 milliseconds, and leave the amplitude unchanged. Now let's run our simulation. We now have two neurons connected together by mutually inhibitory synapses. Both neurons receive constant tonic input, which, in the absence of the connections, would make them spike continuously. But since they are inhibiting each other, we can use a short stimulus to allow one neuron to beat the other and allow it to remain firing indefinitely. This is a very simple form of a polymorphic network. This is just a fancy phrase meaning a network that can have more than one type of stable output pattern. However, what we do not have here is a rhythmic network. To get oscillations, the losing neuron needs to be able to overcome the inhibition of the winner so it can start firing. A simple way of doing this is to introduce a nonlinearity into the system. One neuron spikes and inhibits the other. As the spiking continues, the inhibitory synapse decrements and the inhibition grows weaker until the other neuron escapes and starts to spike. The first neuron is then inhibited in turn, and during this silent period, the decremented synapse recovers back to its full strength, so that when the second synapse in turn decrements, the first synapse is again fully operational, and so on. To do this, go to the hyperpolarizing IPSP synapse and set the facilitation value to 0.5. And the facilitation decay to 50 milliseconds. Now we shouldn't need the second stimulus to switch firing, so let's disable it. This time when we run the simulation, we get a nice oscillating pattern. In this circuit, we still have to inject an initial current pulse to unbalance the inhibition so that the two neurons don't just continue to fire synchronously. This sort of unstable equilibrium is unlikely to happen in real life because all neurons have a certain level of membrane noise. To demonstrate this, disable the stimulus on neuron 1 and see what happens. The two neurons fire exactly synchronously. Therefore, the inhibition that they impose on each other is exactly synchronous, and both neurons continue to spike, but at a much lower frequency than in the absence of the inhibition. This is an unstable condition, like a knife balanced on its blade. We can overcome this problem by adding a small amount of noise into each neuron. This means that pretty soon after the start of an experiment, one or another of the neurons win, and the system unbalances and starts to oscillate. However, because the noise is random, we can't predict which neuron will win, nor precisely when the oscillations will start. Add 0.4 millivolts of noise to each neuron, and then rerun the simulation. This time, the two neurons begin oscillating entirely on their own. We're not providing any stimulus to start them going. Another form of nonlinearity that can allow oscillation is spike threshold accommodation, or post-inhibitory rebound. These two phenomena arise from the same basic mechanism, so they're not different. In this case, the thresholds of both neurons increase during their spiking phases and decrease while they are inhibited. So one neuron spikes until its threshold rises above a certain level, when it ceases spiking and ceases inhibiting the other neuron. Meanwhile, the other neuron's threshold has been dropping back to its base level while it was inhibited. So as soon as it gets released from inhibition, it starts spiking, until its threshold too increases, and so on. To do this, go back to the hyperpolarizing IPSP synapse and set facilitation back to 1 and facilitation decay to 100 milliseconds. Then change the accommodation of the neuron to 0.7 the accommodation time constant to 50 milliseconds, and change the tonic stimulus to 10 nanoamps. Rerun the simulation. Again, we get a nice oscillatory behavior, but using a different mechanism this time. By expanding the network of neurons, it's possible to obtain rhythmic activity from inhibitory circuits without introducing any nonlinearity into the response. Let's open the hyperpolarizing IPSP synapse and change its decay rate to 35 milliseconds. Then remove the nonlinearity we added by setting the accommodation back to 0. Set the tonic stimulus to 8 nanoamps. Delete the synaptic connection from neuron 2 to 1. Copy neuron 2 and paste a new copy of it, and then change its name to 3. Add inhibitory synapses from neuron 2 to 3 and from neuron 3 to 1. Then add neuron 3 to the chart and let's rerun the simulation. We now have 3 neurons which inhibit each other in a ring configuration. There's no nonlinearity of the type we had to introduce previously. None of the neurons accommodates, and the synapses do not anti-facilitate, but the system still oscillates. Notice the phase progression of the oscillation is in the opposite sense to the direction of inhibition. So how does the system oscillate? Each neuron has a small tonic stimulus that tries to move it back to the bursting phase. But at one point in the phase, it is strongly hyperpolarized from the inhibitory synapse. It takes the tonic current a certain amount of time to depolarize each neuron back to their threshold to begin firing. The way the synapses connect to the neurons sets a pattern where each neuron fires for a time until the next one reaches the point where it begins bursting and takes over. It's also possible to create a simple network oscillator using the more abstract firing rate neural models. To do this, add 2 tonic neurons to the diagram. Set the accommodation time to 300 milliseconds, the membrane conductance to 50 nanosiemens, the accommodation to 0.9, and the noise to 0.5 millivolts. Then add inhibitory reciprocal connections that are negative 10 nanoamp strong. Close the old chart and create a new one. Add the 2 neurons to the chart and view their firing frequencies. Set the update interval to 200 milliseconds and the points to keep to 15,000. Run the simulation. The two neurons start out almost synchronously, but soon the noise and inhibition begin driving them apart, and they begin to oscillate. Oscillatory behavior is a very important part of neural control. This tutorial has demonstrated some basic techniques for adding network oscillators to your AnimatLab projects.